let's start out by doing this. What's the absolute value of 5? 5. What's the absolute value of negative 5? 5. So what's the rule for absolute values? Always positive. So my absolute value will always be positive. Negative absolute value of 5. What's that? So sometimes when students hear absolute values are always positive, they think no matter what, if there's an absolute value somewhere in the problem, it's going to be positive. Not necessarily. The absolute value itself is positive, like you said. But in this case, there's an external factor that then makes your number negative. By the way, these are two vertical lines like this, right? These are the absolute value symbols. And they are very much not like parentheses. For example, 2 times x plus 3, that equals 2x plus 6, piece of cake. 2 times the absolute value of x plus 3 is not equal to, I don't even know how you would write this. What are you going to write? Absolute value of 2x plus 6, that's something. 2x plus 6, absolute values, I don't know. It's not equal to any of this stuff. You cannot distribute inside absolute values, okay? Absolute value of x equals 3. What's x equal to? Positive 3, you're saying? Or negative 3? So there's two answers? How about this? Absolute value of x plus 4 equals 7. 3. So we'll say x equals 3. What's the other? Negative 3? Can I get just one answer and then just slap a negative on it? No. You guys shaking your head? No, you can't. I just can't. That's what I did over there. How did you get the 3? How did you get this 3? Like, this is an easy enough problem. You could just look at it and do it in your head. What if you can't do it in your head? The absolute value of x plus triangle equals smiley face. There, solve that. The way that you solve these is the same way you solve this one, except for you didn't know it. What you do with absolute values is there are two answers. One is a positive type answer and one is a negative type answer. So what we do is we branch. So there's a positive branch and there's a negative branch. And in the positive branch, what you do is you just drop the absolute value symbols. X equals 3. That's easy. On the negative branch, what you do is whatever is inside the absolute value, that stays the same. So that's just the x. And then you change the sign on what it's equal to. Now, in the one that we did in the middle, it's easy to see this because you can do it in your head. You can immediately plug in positive 3, see that it works. You can immediately plug in negative 3, see that it works, and everybody's happy. Let's apply the branching to this one. So on the positive branch, we're going to have x plus 4 equals 7. You keep everything the same. You just drop the absolute value symbols. And then on the negative branch, we keep what's inside the absolute value the same. X plus 4 stays the same. But instead of a positive 7, we make it a negative 7. We change its sign. And now you solve each one of these branches independently, just like you would solve anything else from an Algebra 1. Subtract 4 from both sides. So x equals 3, there's one answer. And then subtract 4 from both sides, x equals negative 11. The first move that you really want to do is you need to isolate the absolute value. You need to get that absolute value by itself before you branch. So when you're solving something like this, the first move is isolate the absolute value. Get it all by itself. Your second move is to branch. So let's work on this equation and get the absolute value by itself. We're going to do that by adding 4 to both sides. Now we can branch. So the positive branch is going to be 3x plus 2 equals 8. And we're going to solve that. And then the negative branch is going to be 3x plus 2 equals negative 8. Fantastic. So 3x equals 6, x equals 2. So there's one solution. 3x equals negative 10, x equals negative 10 thirds. There's your other solution. I know when we talked about the definition of an absolute value, and we said, what does an absolute value mean? And you guys were, some of you were kind of like, well, it's a distance from 0, right? That type of idea. If you think about a number line like this, and you do put a 0, you could think, like on this one here, we had the absolute value of 3x plus 2 equals 8. So basically, this guy here is some stuff. We want to know what that stuff is. And you could think of this absolute value is equal to 8. That means that the distance from here to here is 8, and so is the distance here to here to negative 8. And so that's kind of conceptually, when you're tying in the graph, why you branch. Because the absolute value is sort of that distance from 0 in a graphical sense. Initially, I didn't want to toy around with graphs, but we can bring it in now that you've seen the branching. So you've got this absolute value of stuff that's equal to some distance to the left and some distance to the right. Another way you can think about this branching, and I've seen it done this way as well, is whatever you have over on this side, like you've got this equals 8, you put an equals here and you put a negative 8 there. And so check this out. If you try to solve this, just drop the absolute value symbols. So you get negative 8 equals 3x plus 2, which equals 8. So instead of an equation that has two sides, a left and a right, you have an equation that has three sides, sort of, like a left, right, and a middle. How would you solve this equation that has a left, right, and a middle? The rules are the same that apply to regular equations. You can do something, but whatever it is, you have to do it to everything. So how would you get x by itself? What's your first move? Subtract 2, and you subtract 2 from everything. Subtract 2 here, subtract 2 here, subtract 2 here. So now this goes away, and negative 8 minus 2 is negative 10, equals 3x, which equals 8 minus 2 is 6. What's your next move? Divide by 3, and you divide everything by 3. So you divide by 3, you divide by 3, you divide by 3. These go away, and you're going to get negative 10 thirds equals x, which also equals 2, which is the same answer we had before. This statement, this guy right here, and a word of caution, this is not mathematically correct, okay? Negative 10 thirds does not equal 2. There's something called the transitive property of mathematics. It says if A equals B and B equals C, then A equals C, right? Like that idea. That does not apply here. This is a trick that we're using to get at an answer. The reason this is not mathematically sound is because we added this guy right here. And as soon as we put that negative 8 on the other side, we kind of left the realm of proper mathematics, and now we're kind of using a manipulation, a trick, in order to get at an answer. When you're doing these absolute value problems, you can either branch, do the left branch and the right branch, and some students like that, right? It's small pieces. Solve this little one over here, solve this little one over here, and you get two separate answers. Or you could do it this way. Create a mirror image with a negative sign, or the opposite sign, over on the left-hand side, and solve a three-part equation. Let's talk about graphs. So when we talk about graphs, one way you could solve this is to do this, right? Make a table. Fab 5, negative 2, negative 1, 0, 1, and 2, and you plug them in. Should we do this again? What if we plug in 0? 9? Uh-oh. So 5 is not the y-intercept. 9 is the y-intercept. The problem with plotting points is kind of this. Is if we only plot these 4 points, you might come to the conclusion that the line looks like this. Because previously, when we plotted 4 points, it was a line, right? We're dealing with lines. And there's no hint of a V. The only reason you may think that there's a V involved in this thing is because of prior knowledge. You've seen it before. But pretend this is the first time you've seen this. There is no hint of a V. There is no bounce in this thing. And so you would plot 4 points. You can say, well, 4 points were good enough before. I got a line. Why aren't 4 points good enough now? But what if you kept plotting points and you plotted more and more points? Or if you learned how to read this equation? Before we actually answer this one, let me start you out with a simpler model. Okay, so I'm going to get rid of all this. We'll come back to it. But what would the graph of y equals the absolute value of x look like? And to answer this, we're going to start with y equals x. So and this is simplest case, right? Y equals x. What does the graph of y equal x look like? Oh, it looks like that. That's the graph of y equals x. It has a y-intercept of 0, 0. on a slope of 1. So here is the graph, and we'll draw it the best that I can, freehand, something like this. Okay. This is the graph of y equals x. That's the red graph. Okay. Now let's graph the absolute value. What does the absolute value do to a number? Makes it positive, right? Absolute values are always positive. So when you have a value here that's positive 5, what's the absolute value of positive 5? Positive 5. What about positive 4, positive 4, positive 3, positive 3, positive 2, positive 2, positive 1, 0, 0. What's the absolute value of negative 1? Positive 1. So this point gets bounced up here. The negative 2 gets bounced up to positive 2. The negative 3 gets bounced up to positive 3. The absolute value takes negative y values, or negative y coordinates, and makes them positive. This blue line is the graph of the absolute value of x. So the basic graph of a absolute value is a v. What would happen if I took this absolute value of x, y equals the absolute value of x, and I added 2 to every y value? Every y value, I'm now going to add 2 to it. What's it do? Yep, shifts it up 2 units. So this point gets 2 added to it, this point gets 2 added to it, this point gets 2 added to it. And our focus is going to be, our focus is on this point right here. This is called the vertex. Parabolas have vertexes too. Vertex is kind of a generic term for like a local minimum or a local maximum. So that's the vertex. The vertex gets shifted up 2 units. So when we add or subtract a number exterior to the absolute value, it shifts it vertically. It shifts it up and down. We could call that k. K because it's a vertical shift, up and down. Let's say that we have the absolute value of x plus 3. What does that do to our graph? Plus 3 on the inside shifts it 3 units to the left. What's this graph look like? Where is its vertex? If I start with my standard graph, zip, zip, like that guy, and here's my vertex, how do I move the vertex? Up 5 units. 1, 2, 3, 4, 5. Where's that come from? Here. That means move the vertex up 5. And now my horizontal shift, this plus 4 means move it to the left 4 units. So 1, 2, 3, 4. So this should be a picture of that graph. How do we know we're even right? I don't know. Let's go back to the graph. Maybe I'm totally wrong. So we'll say the absolute value of x plus 4 and then plus 5, right? And if we've done this right, I think I can zoom out a little bit. How's that? Does that look like that? So here's the generic format of this. Y equals the absolute value of x minus h plus k, where h is your horizontal shift and k is your vertical shift. There's one more thing that we need to add to this actually to make it complete, and that's a factor of a out in front. You can have a multiplier out in front. And what a does is a controls 2 things. First of all, if a is positive, then your absolute value opens up. And if a is negative, then your absolute value opens down. So the sign of a determines whether it opens up and opens down. And if you've had graphing of parabolas before, this probably sounds familiar. It's the same thing that we'll learn at the rules for parabolas. The value of a, and I got to write this as a definition, so hang with me. If the absolute value of a is greater than 1, then you have a narrow absolute value graph. It makes it more narrow. It closes it up. If the absolute value of a is between 0 and 1, then your absolute value graph gets wider. And really what we're talking about is the slope of the line. Does it open up or does it open down? That's determined by the sign. And then whether it's narrow or wide is determined by the absolute value of that sign. What happens if a becomes 0? Yeah, all that stuff, absolute value of x minus h goes away, pow, it's gone, and you're left with a vertical shift, and it's just a straight line at k. So it'd be like y equals 6, and y equals 6 looks like this. This is y equals 6. So you're going from this to this to this to this, and it would be so much cooler if I had slider bars and an animation to show you this. The reason this is so important to learn this stuff, this guy here, the reason this is so important is because we're going to see it again. We're going to see it with parabolas. We're going to see it with cubics and rational functions. This h and k stuff, we're going to look at it with conics, circles and ellipses and hyperbolas. We're going to rewrite everything in terms of h and k and get you used to the idea of moving this vertex point around. Slope-ish? We'll say slope-ish. It's kind of slope-ish because this is actually the slope of this leg of the, well, I guess this leg is going to have slope equal to positive a, and this leg will have slope equal to negative a. I was going to show you this yesterday, but I didn't because I guess I wanted you to see this part first. Check this out. This is another format of a line. You can play the same game with a line. So what does your standard line look like? The standard line, I think we started out with this, right? Like something like this. Bloop. And when you start with a standard line, it's hard to say where the vertex is. Like with absolute value, you know where that vertex is. It's like right there. It's the bottom of the V, right? And with a parabola, it's the same thing. Where's the vertex on a line? Don't have one. But you do kind of. It's here. So what if I were to give you the equation y equals 2 times x minus 4 plus 3? What's your vertical shift? Vertical shift, up, down. Up 3. So I take this line, and again, slider bars, imagine, right? 1, 2, 3. So now I've shifted this line up 3. Okay, so this is the k equals 3 shift being applied. What is the horizontal shift? To the right, 4, right? Because it says minus 4, so now we got to go to the right 4. So we're going to take this and we're going to shift it 4. 1, 2, 3, 4. So this is shifting h equals 4. So now our line is looking like this. So we've applied 2 shifts, a shift up and down, or a shift up, and then a shift to the right. And now, what is the slope of this line? The slope of the line we have drawn right now is 1, but the slope of the line in question is 2, right? So now we got to take this, and instead of having a slope of 1, which goes off like this, and let me erase this. Can I just say we shifted it, okay? So let's get rid of this other stuff. So now instead of a slope equal to 1, we want a slope equal to 2. And that's going to look like this. Is this line? And your brain says, I don't know, because I only recognize stuff that's in y equals mx plus b. So could we transform this into y equals mx plus b? I could also graph it on the software and see it. But let's do it this way. So you're gone. 2x minus 8 plus 3, 2x minus 5. Now you're in y equals mx plus b format. What's your y-intercept? What's your slope? How about that? You don't even need to know y equals mx plus b. If you know h and k and a, if you know that format, you basically apply horizontal and vertical shifts to the standard model of a line. Standard model meaning it goes through the origin and it has a slope of 1. Have you ever seen this before? Usually you get into the h and k modeling when you get into parabolas a little bit, completing the square, you'll see that, and especially when you get into conics. It's not usually employed at this level because really this h and k idea is more complicated than just y equals mx plus b. You gotta admit, y equals mx plus b is pretty simple. Sometimes it's nice to take a more advanced concept and retrofit it to simpler concepts that you already know. Graph s of x equals the absolute value of x minus 4. And now when you see this, y equals the absolute value of x minus 4, maybe something's tingling in your brain. Now you're not thinking, oh, I got to make a table and graph and blah, blah, blah. What do you see when you see this equation now? It's going to be shifted down 4, and it's going to be a V, right? So here's your standard absolute value graph, and you're going to take that guy and you're going to shift it down 4 units. Why? Because of that guy right there. Is there any horizontal shift? No horizontal shift because there's nothing inside with the x, right? Is there any slopey change? No, there's no slopey change because there's no, the number out front here, if you wanted to be technical about this, we would say this is 1 times the absolute value of x plus 0 minus 4. If you wanted to show the hidden symbols that are there. What is your up and down shift? 4. So this is your vertical shift. What is your horizontal shift? 0, which means it doesn't move, right? And what is your slope? So this slope here is positive 1, and this slope here is negative 1. See, check that out. It is. That's negative 1. That's a slope of negative 1. And this is a slope of positive 1. Pretty cool, huh? So you're starting to read this a little bit more. And you'll practice this, right? You start doing your homework. And you start seeing this stuff, and you're like, oh, I kind of start to recognize that now. And you start to think a little bit differently about this. Instead of thinking, I'm going to make a table and plot a whole bunch of points and make mistakes in arithmetic, I'm going to instead shift it H and K. Now we got the graph. The blue one is the graph. We don't need the standard anymore. This is the graph. And I could pull it up on the computer and show you, but we're good. All right, let's answer some of these questions. Where is this function increasing? Over what domain is it increasing? I can identify the segment of the graph. This segment right here. This is it. This is where the graph is increasing. The other part of the graph, it's decreasing. And remember, we're talking about moving left to right. As you move left to right. As you move left to right from here, you are going down. Decrease, 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 decrease. As you move left to right past 0, you're increasing, 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 increasing. The answer is 0, comma, infinity. From 0, open dot, to infinity, this function is increasing. It's decreasing, and I'll do this one in blue like this. Here's where it's decreasing, right? That's where the function is decreasing in value as you go left to right. This is going to decrease on this interval, negative infinity to 0. Negative infinity is out here. 0 is right there, and here's positive infinity. What if the graph really looked like this? And I'm going to say this is negative 5 right there, okay? Where is the interval where this function is increasing? Negative 5 to infinity. Where's the graph decreasing? Negative infinity to negative 5. In the computer software, you type 2 lowercase letter O's to mean infinity. So again, if we go back to the graph of this guy, and notice these instructions down at the bottom. If any of the above does not exist, leave it blank. So does this graph have a maximum? And when they say maximum, they mean a maximum y value. No, it doesn't. The y values keep going on to infinity, right? Like forever. Okay, so it has no maximum. Does it have a minimum? Yes, it does. What is that minimum? The minimum is negative 5, and that occurs when x is equal to 0. So when x is 0, the y coordinate is negative 5. That's your minimum. What is the domain? The domain are all the possible x's. So how about negative infinity to infinity? That's the domain. What is the range? What is the smallest y value? Negative 5. What is the largest y value? Infinity.